Profound words. Similarly, an electric field is going to exist around a charged object, regardless of what else is going on there. So we analyze I have two electrically charged objects. Look how they interact with each other. And now we're going to go to what does one do by itself? Okay. So we're going to start this process here. I've got a mass. Gravitational field reflects the mass, or the effect that a mass has on the space around it. We've already established gravity doesn't exist. Space-time's curved. So basically what we're analyzing here is how does the mass of an object warp space-time around it? That's effectively what analyzing gravity does. Electrostatics is a little bit different. Charged objects don't warp space around them. They have a measurable electrostatic field or electric field. So just like if I had a mass, using classical physics, we can analyze it and say, yes, there is a gravitational field, looks like this. And if I put another small mass there, we could say, oh yes, this thing has gravitational field going this way. This guy has a little bit gravitational field going this way. But ultimately what's going to happen is that these guys are going to be attracted to each other based on the interactions of their individual gravitational fields. So the force due to gravity was given to us by this equation here, big G mm over r squared. The definition of the gravitational field was just this portion of it here, big G m over r squared. We're going to look at we're going to ignore these guys. It's these two relationships that we're going to equate things to. We're going to skip example 2 because you've done gravitational field strength and gravity field. Flip the page.
Does that sort of like how wireless charging works?
Yeah, induction is how wireless charging works. We'll get there in the last chapter. So, similarly to gravity, we've already established that the electric force is given to us by the following equation. We didn't go into how it was born, but the force electrically between two charged objects is given to us by this, kqqq over r squared. And it's not super useful to have that other equation on the previous page. It's more useful to have it on this page. So we're going to put it here, gmm over r squared. And just like we said, well, if this is the force due to gravity on another object or between two objects, and I have little g, the gravitational field strength for any one of those objects, likely the more massive one given by that, the definition for the electric field is going to be what, do you think? Kq over r squared. This guy here is going to be the definition for the electric field, big E, for a singularly charged object. Just like we analyze gravitational fields, so now we can analyze the electric field for a charged object. This can all be found at the bottom of your formula sheet right here. This whole bottom piece is all E and M.
Wait, not that much.
Okay, so we had this one we introduced yesterday. Total charge Q is equal to N, the number of charges times the elementary charge. We had this guy here, lesson 2, F equals KQQ over R squared, the force between two electrically charged objects. And now we got this guy here. The electric field strength of a single charged object is equal to K times Q divided by R squared. And you can kind of see where we're going here. Oh yeah, it's going to be good. It's going to be good. Yep. Tirith, yeah, you really got to go. I suppose you can. Well, that's, yeah, because. So, let's put some box stuff in here. E equals KQ over R squared. Oh, no, I'm going to flip back here for a sec. Yeah, the things that we scribbled out, we're actually going to do this. The gravitational field as a ratio g, little g, we had that the force of gravity is equal to mg. So we can look at how little g is just going to be the force of gravity divided by the mass of that object. This is, though, the result that we're going to use on the next page. So we had Fg equals mg, where little g is equal to gm over r squared. If we flip this thing over here, we've got that F equals kqq over r squared as the force. But we also had that the electric field is this kq over r squared bit. So what we can do is we can say that my Fe, electric field, instead of kqq over r squared, we can replace this kq over r squared with the, oh, sorry, I'm pointing at things you can't see. This kq over r squared with E, where E is the electric field strength. So we can say now that my electric force is going to be equal to some little particle q, charged particle q, times the electric field that it's interacting with is going to give us the force on that little guy q. We can rearrange this and get that my electric field strength is equal to the force that a charged object is experiencing divided by that charge q. So this particular relationship here, not the ratio one, the ratio one is kind of cumbersome, but this guy here, this Fe equals QE, I'm going to add that to my formula sheet. By adding it, I'm just going to point out its existence. It's right there. We got this guy here, this guy here, this guy here, and this guy here are all related to the charge on an object, the force, and the electric field. So these four concepts are all very closely related to each other. The units of electric field, if we look at this, a force has to be measured in newtons. Q is measured in coulombs. So to make the units work out properly, this is newtons, this is coulombs. So my electric field has to have units of newtons per coulomb. It's got to cancel out the coulombs and give me newtons equals newtons. If we think back to the units of gravitational field, the units of gravitational field are newtons per kilogram. So coulombs are a property of charge. Kilogram is a property of mass, but they are related conceptually. How much of something, or how massive are you? How charged are you? And based on those two things, there's a whole bunch of implications that fall out. Again, just like with force, electric fields can't be negative. That doesn't make sense. So we're going to use the positives and negatives to determine the direction that the electric field is acting in. In 2 pages. So we, just like with electric force, we'll make a note down here. Do not include the positive or negative on Q. We're going to use it to determine direction. Okay. And I'm going to sum, there's a whole bunch of rules involving when to use positives and negatives and when not to use positives and negatives. I'm going to sum all, or I'll collect all of that at the end of this unit into one nice little page. Flip the page. So, at a certain point in space, a negative 0.5 microcoulomb test charge experiences a force of 5.2 times 10 to the negative 4 newtons towards the south. find the electric field strength at this point, and then B, find the electric field strength 0.45 meters right of a 2.3 microcoulomb charge. A and B are totally disconnected questions. This isn't one of those previous examples where you need A to do B, to do C, to do D, and they kind of hold your hand the entire way. A and B, entirely unrelated to each other, so let's treat them as such. Let's do A. Sorry?
In space, there's 7.
Okay, when they say in space, they don't literally mean space. They mean in a space that has been made available for the experiment. This is what's going on.
Oh.
In a space, I'll add an A in there to make Joseph happy. So, I've got my test charge there. We are told that Q equals negative 0.5 times 10 to the negative 6 coulombs, and we're told that this thing experiences a force in this direction. It would have made more sense to say down, but whatever. F equals 5.2 times 10 to the negative 4 newtons. What's the implication here? Read between the lines. What must be true? There are two things that one or the other could be true based on what we've been told. Nathan. Well, that's true. It's not what I'm looking for.
Or your electric field's going to be going in the opposite direction.
Even more basic than that. For this thing to experience an electric force, what must be nearby? Not another force. Another charged object. Either you have a positive charge located somewhere. If it's positive, where is it located? This charge is negative. If the charge is positive, the force between the positive charge that we can't see and this negative charge is going to be attractive. So the positive charge would have to be where? The positive charge would have to be down here somewhere. Or, for this thing to experience a force downwards, what must be true? Nathan. There could be a negative charge up here that we can't see. One of these, either one, is true. So there's an implication here. There's an implication that somewhere there is another charge creating this electric field that this thing's interacting with. At this point, we don't care about it. But it's important to recognize that that's what that's implying. So we want to know what the electric field strength at that point is. Well, we've got a handy-dandy relationship. The electric force on some charge Q is equal to the charge on that charged object times the electric field strength that it's interacting with. So we know the strength of the force is 5.2 times 10 to the negative 4. The charge on my object is 0.5 times 10 to the negative 6. Again, I do not include the negative because the negative is just connected to the direction of things. Times E, my electric field strength. So how big must my electric field be in order to provide that charged particle with that force? 1,040, and we need units. Newtons per coulomb. Cool. That's a pretty substantial electric field, actually. Yeah. That is not an insignificant electric field. Normal is relative to the situation at hand. Well, actually, it's an interesting question. Like we could have calculated the only time that most of you have actually experienced an electric field of any intensity was yesterday, when you walked past the object and felt the tingling. That was you interacting with an electric field for a not insignificant electric field for probably the first time in a long time, perhaps ever, depending on how your science teachers in middle school played with this stuff.
I had a friend, and I don't know if that's...
But it's the idea that it's not the shock, it's the you walked through it and you felt the effects of something you couldn't see or touch and that wasn't touching you. You interacted with an electric field. You moved in and out of an electric field. Those of you who walked by. Yeah, I mean, yeah. As long as the holding above is what would, it would be a small electric field there. So let's do B. Again, totally disconnected. We want to find the electric field strength 4.5 meters to the right of a 2.3 microcoulomb charge. So I've got a charge here. Q on this guy is 2.3 times 10 to the negative 6 coulombs. And some point in space over here, we're told it's 0.45 meters to the right. I want to know what E is there, created by that charge. We're not given anything like a force. We're just told you have got a charged particle. It's just sitting there. What's the electric field strength over here somewhere? So instead of using this ratio, Fe equals QE, we're going to have to use the other expression for E. We're going to use this guy, that E, my electric field, is given by K, that universal constant, times Q, the charge that is generating the field, divided by the distance from that charge squared. This is the same way we would find the gravitational field strength around some other massive object. So I've got 9 times 10 to the 9, 2.3 times 10 to the negative 6, divided by 0.45 squared. And Nathan, this is why it's hard to answer the question, what is a normal electric field? Because the value for this electric field strength is what, guys? Figured Ashton and Zach were like zipping along. Here we go. 102,222 newtons per coulomb. Also, not an insignificant electric field. I'm just going to Google it. I don't even know how to begin to estimate that. There's lots going on there. Electric field. Field is not spelled with an R. Generated by Van der Graaf.
So small. I mean, at least with plants. I mean, a little tiny baby second. Yeah, the flash. Yeah, he must. He just really fast. Yeah.
Okay, so this isn't gonna do it. Maybe I can do a quick conversion for you here. Theoretically, okay, assuming that this thing is maximally capable, your average tabletop generator can generate that divided by, how far away were you? No, you were like... Well, touching it grounds it out, negates everything, because there's no charge building at that point. Let's say that you guys were like 0.6 of a meter away. The electric field strength that you guys were experiencing yesterday, assuming you were touching it, but walked by it, yeah, about 2 feet out, would have been larger than this one even. 166,666. I mean, that sounds exact, but approximately. That is the maximum, apparently. A maximum electric field that a Van de Graaff's going to generate at about 60 centimeters. The information I'm using uses voltage, which I haven't taught you guys about voltage yet. But they can generate about 100,000 volts. It's a lot of volts. The tabletop version, the one we were playing with yesterday, can generate a voltage of about 100,000 volts. Oh yeah, there are like monster versions. Like you just make them bigger. The bigger they are, the larger the charge you can produce. You could toss one in the back of a like on a flatbed truck and just make the whole apparatus larger. And now why? Well, as you this could be a fun little experiment. Driving down the road, you could attach the wheels on the vehicle to a drive shaft that would connect it to the belt that's spinning there. So the faster you go, the larger the charge that's generating on the thing. And you could just spontaneously like just zap things as you're driving by. Why you'd want to do that, I don't know, but it's totally possible. Okay? So these numbers are not insignificant, but I mean they're not insignificant because like the size of the things that are interacting with them typically are very small. You're dealing with electrons and protons that are interacting with electric fields, or small charged particles that are interacting with their electric fields. Like I said, the one that you experienced yesterday is on the order of twice as big as this. Okay? Flip the page.
Let's go.
So the direction, we're going to talk about direction now. The direction of an electric field. With gravity, this was never an issue. Gravity always acted in. Because you only ever have one kind of mass. Mass. Okay? You don't have anti-mass. Well, yeah, because you've got positive charges and a corresponding opposite, right? Like a proton has a positive charge of 1.6 times 10 to the negative 19. Thank you, Nathan. But the electron has negative that. That's just the idea behind a positive charge and its anti-charge. They are equal and they are opposite. So we never looked at gravity and antimatter because that's weird. Because gravity always attracts. Property of mass creates a gravitational field, it always attracts. But we know electric fields don't always operate that way. Depending on the polarity, the positiveness and negativeness of the things that you're dealing with, we know that if I have a positive charge and a positive charge, they're going to repel each other. But they repel each other without touching each other, so that means their electric fields have to be interacting in a way that forces them apart. That's weird. When we have a positive charge and a negative charge, their electric fields have to be interacting in a way that produces an attractive force between the two. So we're gonna have an electric field that is operating in one direction or the other, depending on the polarity of the charged object. When I say polarity, I just mean positive or negative. The way that this has been defined, okay? So physicists back in the day, when you're first discovering this, they just had to make a decision. They're like, okay, so we're going to call this thing positive, because it doesn't really matter. It doesn't matter if the electron's positive or the proton's positive. One's positive, the other is the opposite. It doesn't matter if the physics is all the same as if you just flip the signs.
So are electrons not negative?
Well, they have been defined to be. So yes, they are. It's like you guys did you did current last year, yeah? In Physics 11, we all did current. Nodding our heads. Okay, did you guys talk about the difference between current and actual flow of electrons?
Oh, is that like the
You should have. Hannah's nodding her head. Okay, so there was a little bit of circuits. There should have been some circuits. Current, they were like, yeah, current's totally this way. But then when they discovered that it wasn't actually the positive charges that were flowing, that it was the negative charges that were doing the flowing, and the positive charge, the protons, were staying put, they're like, oh, well, we screwed this up. Instead of just, rejigging all of it, we'll just say, you know what, the electrons are actually negative. Current is going to be that way, but the direction that the electrons are actually flowing is just going to be the other way. And we're just going to understand that to be true and move on and not actually change anything. Okay? That's what happened. Yeah, they're just like, rather than redo all the work, we'll just understand and agree on this is to be true, and we'll just move forward. Similarly, when they're coming up with this, analyzing electric fields and how these things interact with each other, they have to say, okay, well, one's going to go one way and one's going to go the other way, but what does it actually mean? So we're going to define it to be the way I'm about to show you. To figure this out, what they did was, let's say I have some charged objects. They could be positive, they could be negative, whatever. What would happen if I took an imaginary, tiny, positive charge and I let it go? What would happen? Okay. They defined the electric field to be in the direction that that positive test charge would go. Turns out it doesn't actually matter. They just had to make a choice and go for it. And that's what they chose. So, if I have, we're told, so here's the question. We want to find the direction of the electric field at a point where a 0.5 microcoulomb test charge experiences a force of this. We've already done that question. That was the previous question. That's our test charge. It's experiencing a force downwards. This test charge is negative. We already went over the implications of this. The implications are, if that test charge has a force downwards, then what must be true? There has to be a large positive charge there or a negative charge above it. We've done this one already too. I've got some positive charge here, Q. I've got electric field strength out here this way. Okay, we found the electric field strength. We know that the electric field at that point is equal to the value that we found before. It's 102.222 newtons per coulomb, and we need a direction. In order to determine the direction, we take a positive test charge and we place it at that point. Positive test charge is going to go which way at that point? If this is positive and I put a positive test charge here, screaming off to the right very quickly. Okay? So because that is where, or that is the direction a positive test charge could go, we say that the electric field has a direction at that point to the right. So let's extrapolate that. If I have a positive charge here, and I place test charges all around it, I can generate, in this case it'll be two-dimensional, but theoretically a three-dimensional version of the electric field around a positively charged object. If I put a positive test charge here, which way is the electric field going to go? This is positive, this is positive, positives repel. Positive charge is going to go screaming upwards. So we say that the electric field is in that direction above the thing. Over here, on the right, which way would a positive charge go next to this positive charge? Go to the right. This guy down here. This guy over here. This guy up here, top right. Gonna go that way. Bottom right. Go that way. That guy down to the left. This guy up to the left. Okay? So that's a positive charge. So then a negative charge, what's going to happen? What would you think would happen? Exactly the opposite. Yeah. If I put a positive test charge anywhere around this guy, it's going to go in. So that must be the direction. That is what we're going to define to be the direction of the electric field around a negatively charged object. It's going to go in. No, to determine the electric field, the definition was, what's the direction a positive test charge would go? Which means that a negative test charge goes the opposite direction of the electric field. So the direction of the electric field, as defined by this particular mental experiment, is out of a positive charge and into a negative charge. Flip the page. This question looks very similar. We just did it a couple days ago, except we did it with gravity. Okay? I had the Earth, I had the Moon, there was a point between them. What is the gravitational strength at that point between these two massive objects? We're going to do exactly the same thing here, except it's going to be what is the electric field between these two charged objects. The procedure is exactly the same. I want to find the electric field and direction at this field point right there. So we're going to analyze it using what we've just established. So I'm going to color this guy in green. I'm going to color this guy in pink. To help me identify what's going on here. Okay, this green guy, positive charge, the field point is right there. What is the direction of the electric field caused by the green guy at that location there? Just the direction. At that point right there, Nathan. You're right. From this guy, it's going to go outward in every direction, but I want that point right there. Straight to the right. So he's going to have an field point going this way. Or an electric field going that way. This pink guy is going to have an electric field going which way? He's also positive. It's going to go to the left. Which one of those is going to be stronger, do you think? The one that's closer. Why? How do you know that so easily? Because the charges themselves are equal. So the only thing that we're changing here is the distance between them. That green guy is going to be likely stronger than that pink guy because he's closer. So then the net electric field is likely going to go in which direction? Likely to the right. So I'm going to call that direction positive. And we'll see at the end of all things if we were correct. So the strength of the electric field at that point from this green guy is given to us by E equals K times the charge of the green guy divided by how far away from the green guy we are. So K is 9 times 10 to the 9. The strength of the charge is 1 times 10 to the negative 6. Again, I do not include the signs. The signs have given us the direction. Now we can stop using them. Crystal, you mind grabbing that? And the radius is 1. What was that, Crystal? Ah, awesome. What's the value? 9,000. Not over 9,000. Exactly 9,000. Newtons per coulomb which way? To the right. Now I know which ones of you have watched Dragon Ball Z. Pink guy. E equals KQ over R squared. K is a constant, 9 times 10 to the 9. The charge is the same, 1 times 10 to the negative 6. The only difference here now is the radius has changed. What is the distance? 3. The total distance charge to charge is 4. That's 1. That's got to be 3. It's a good thing. He's trying to save himself. What is the... One more time? 1,000. Good. 3 squared.
Oh, yeah,
Newtons per coulomb to the left. So then the net electric field, E net, is just the sum of all my electric fields. To the right we said was positive, so it's going to be 9,000 minus 1,000. It's going to give us a net electric field of 8,000 newtons per coulomb to the right. Cool? Relatively straightforward?
I thought it would have been like
This, okay, careful. This is not like a physical object bouncing back and forth between these things. It is not it's not an actual positive charge. It is an imaginary test charge was theoretically placed there. What's the direction of the field? We're going to draw a couple approximations before we draw the full thing. Let's talk about the resultant electric field. So I'm taking, instead of just, now I've got these two, here they are, two positive charges, they're equal. Now I want to go just direction and approximate net strength everywhere. Here we've already established that the electric field is going to be which way? It's going to be to the right, because the guy on the left is going to overpower the guy on the right, and his electric field is out. So this one, conversely, is going to be in which direction? To the left. Everything you own goes in a box to the left. No Beyonce fans here. Okay, cool. Right in the middle, Ashton. What's going to happen right in the middle? Something's going to happen.
Or like they're gonna cancel.
They're going to perfectly cancel each other out directly in the middle. So my electric field at that point is going to be 0. How about right there? It's not going to be 0 anymore, because this guy is going to have an electric field going which direction? This guy's going to have an electric field going which direction? So if I want to add vectors, I got to move this guy tip to tail. So he just goes. That's going to give me, just already said it, so did Nathan, a electric field straight up. So then conversely, right there, it's going to go which way? Straight down. So then interestingly, what's going to happen right there?
Go
up and to the left. Why up and to the left?
because I imagine that second thing on the would also have a little bit.
He's going to kick him a little bit to the left.
So it's not going to be perfect.
It's not going to, yeah, it's not going to be 45. This guy's flinging him straight up pretty hard. This guy's giving a little push to the left. So he's going to look something like this. Okay, based on those 1, 2, 3, 4, 5, 6 dots, we're going to draw everything. Here we go. Let's draw the easy ones first. Careful, follow along with me here. Between two positive charges, the easy ones to draw are the ones that are going out to the left and to the right. On this side, what's the direction of the electric field? Over here? To the left. This guy is going which way? Hey, we like those. Those are nice and easy. The rest of these are going to get really hard. So, let's think about it. I've got 2 going into the middle here, but I've got a 0 in the middle. So what must be happening? How can something go towards 0, but then, you know, it's 0 right there, but it's not 0 anywhere else? What mathematical structure is this going to look like? No, don't do that. That's bad. Don't do that. No. I want a line that approaches something going this way. You're getting warmer. Oh, there it is. The electric field is going to look like an asymptote. It starts going this way, and then it's going to start going screaming up that way. Conversely, this guy is going to go up that way. It's also, yes, Joseph, going to go this way. Okay, you can kind of see what's happening here. If I look back at this guy here and I say, okay, he's going out all the way in every direction, and I'm just bringing another one of these positives in here, you can see kind of what's happening. These lines are going to start to butt up against each other and cause them to bend up and down. So yeah, with two, well, in this case, you're not dealing with electric field, you're dealing with magnetic field, which I'm going to show you later, very similar. But that's what's happening with the magnetic field. The reason that there is that repulsive, with the same polarity of a magnet, is what's happening. It's the electric, or the magnetic fields in that case, that are pushing against each other the exact same way. So then this, let's fill it in. It's going to end up looking like this. Yeah, because as you get further away, they will bend because of the impact of the second force here is what's going to cause these things to bend. Eventually, there will be one straight down. There has to be. There will be a sum of the vectors that does lend it to go straight down. It'll start probably going out to the right here, but it'll eventually curve down. Because something looks like that. It's awful. And right in the middle here, there is no electric field because the electric fields are acting, they're functioning as physical asymptotes. It's pretty cool. This was the third year version of this stuff was my favorite course in my physics degree. It's awesome. It's I can show you. It's over there in that box behind Lucas. The box behind Lucas, that's all my physics, that's all my university work. Oh, because I'm going to scan it and then get rid of it. Yes. The things that you covered make less sense, but the things that get exposed are like, what the frick is going on? Positive and negative, equal and opposite. This one's nicer. Yeah, at every point along the way, this positive charge here in the middle zone is pushing to the right, and this negative is pulling in to itself. So this one's going to be nicer to draw and more typical of what you might think. Positive goes out, negatives go in.
Oh, I remember that.
There will be one that goes straight out that way. There will be one that goes straight in this way. Well, there has to, like, on the axis that punches right through the middle of these charges, this guy's going to be pushing straight left, and this guy's going to be drawing straight right. So this line will be flat. There will be a section of the electric field that goes straight left and one that goes, from this way. But the vast majority of these things are going to end up curving.
So things from this side all the way from the opposite side?
Yes, to a point. We know this is true. E equals KQ over R squared. So this R squared thing, the strength of the electric field falls off pretty quickly. Eventually there's going to be some zone out here where there's no detectable electric field, because as you get further away, it dissipates down to nothing as the limit of R approaches infinity. Mathematically, you're out at infinity, but physically, it doesn't have to be very far for it to be effectively zero. So for those of you who just say, oh yeah, physics is just word problems. Well, it is, but then we abuse the math pretty hard. But math is like, but this is true. And we're like, we don't care. Just don't worry about it. That happens a lot in physics. Okay? So you get diagrams look like this. Okay, I'm going to sum up what we've just established. Flip the page. Here's the summary. The electric field can be found using the definition. If you know the charge and the strength of a force, you can find the electric field using big E equals F sub E over Q. The strength of the force divided by the charge that the force is acting on is going to give you size of the electric field. We could also find electric field strength using this. E equals KQ over R squared. Conversely, instead of finding the electric field, maybe I want to find the forces. The force between two charged objects is going to be given by this. F equals KQQ over R squared. And if I don't know the second charge, I just happen to know that there is an electric field present, whatever is generating that electric field, we're going to get that the force is going to be equal to QE. Flip the page. I will tell you what your homework is. I'm not going to cram the lesson down your throats in the last 5 minutes. We will give you a question of the day following the handing out of the homework. Okay, I want you guys to do question number 1. I want you to do question number 6. I want you to do 8. I want you to do 10. I want you to do 11. I like 15. And I like, ooh, that's a good one. 16 and 18. 16 was the one I was going to assign anyway, but then I looked at 18 and I was like, ooh, yeah, we should definitely do 18. Okay. Yes, I know there's 5 minutes. You can choose to do whatever you want these next 5 minutes. You want to work on the homework? Work on the homework. You want to pack up early? Pack up early. I can't dismiss you, but, you know, do what you're going to do. You do. I'm going to ask the